Good morning, our students, and welcome to this morning's class. This morning, we are about to discuss with you a very important topic in statistics and equally in probability called bivariate distribution. Bivariate distribution. Bivariate distribution. Bivariate distribution. So the question is, what is meant by bivariate distribution? What do we use the concept of a bivariate distribution to do in statistics and probability? Of course, the bivariate distribution is a statistical method or approach with which we can show the probability of two random variables, say x and y, occurring together. That is what we use the concept of bivariate random variable to do. A statistical approach or method through which we can show the probabilities of two random variables, say x and y, occurring together. That is the idea of a bivariate random variable or bivariate distribution. And then, of course, this bivariate distribution can be of two forms. They can be of two forms in the sense that the random variables x and y involved can either be both discrete or both continuous. And in that case, we have what we call bivariate discrete distribution and what we call bivariate continuous distribution. So the two forms of bivariate distribution are: one, we have what we call bivariate discrete distribution, and then what we call number two, bivariate continuous distribution. Continuous distribution. Like already had hinted, we describe it as bivariate discrete distribution if the two random variables involved, x and y, or if the two random variables x and y involved are both discrete in nature. When both of them are discrete in nature, we describe the distribution as bivariate discrete distribution. However, when the two random variables x and y involved are both continuous in nature, we describe the distribution as bivariate continuous distribution. Today, for now, we are going to concentrate our discussion on bivariate discrete distribution. So you permit me to clean this continuous while we discuss this one together, beginning from its joint distribution down to conditional, down to marginal, and down to marginal CDF, if time permits us. So we are now talking about bivariate discrete distribution. Then we move together. He said, let x and y be two random variables. Let x and what? And y be two random. Let x and y be two random variables defined on the sample space S. Defined on the sample space what? S. Of a random experiment. Of a random experiment. And let another function given as x, comma what? Y, be defined on the same sample space of that random experiment, such that this function x, comma y takes up values x what? I, comma what, yj on x and y plane of the sample space. This function x comma y is described as bivariate, or what we call two-dimensional random variable, or simply bivariate random variable that takes observations si, yj. Therefore, the observation that it takes is equally bivariate in nature. What this means is that this random variable x takes a value xi, and this random variable what y takes a value what yj. So x and y are two individual random variables defined on the sample space x of a random experiment. Then a function x comma y is also defined on that sample space, such that this function x comma y takes a value xi comma what yj. This capital X comma y is defined as a bivariate or a two-dimensional random variable, while this xi comma yj is the outcome of this function on that sample space. Of course, we should know that just like the random variable x has its own distribution, and then of course the random variable what y has its own distribution. Equally, this x comma y is also a random variable, and it has got to have its own distribution. And the distribution of this capital X comma y is what we describe as bivariate discrete distribution. We describe it as what? Bivariate discrete distribution. Or we can equally describe it as what we call the joint probability mass function of x comma y. So while x takes a univariate distribution, y takes a univariate distribution, this capital X comma y takes a bivariate discrete distribution, or otherwise called the joint probability mass function of x comma y. So that is actually how this bivariate discrete distribution came to be. Situation whereby we have two random variables, x and y, defined on the sample space. These x and y are, of course, a discrete distribution in nature. Then there is a function, capital X comma y, that takes observations si comma y j from that sample space. We now say that this is what? A bivariate or a two-dimensional discrete random variable, and its distribution is given as bivariate discrete distribution or joint probability mass function of s and y. So the next thing is, having explained what we mean by bivariate random variable, or what we call two-dimensional random variable, how do we define the bivariate discrete distribution or the joint probability mass function? So I'll clean here and then write it on the board while we now start from there. So permit me to clean here. So what we have here now becomes what we call the joint probability mass function. Permit me to write it as a joint PMF. This PMF, of course, is a probability mass function. The joint PM what F. Now, the question of interest is, we have already known that this is what we refer to as the x comma y is what we refer to as a bivariate random variable, or what we call the two-dimensional random variable. How do we write its probability distribution function? Look at what we do. When we define a probability this way, probability of xi comma yj, which of course is the same thing as probability that capital X takes a value xi and capital Y takes a value what? Yj. Which of course is still the same thing as saying probability that capital X takes a value xi intersection that capital Y takes a value yj. When we define probabilities this way, such that these probabilities satisfy these two conditions. Number I condition, the probability that xi, yj is greater than or equal to 0, and ii, the sum over I, sum over j of p of xi, yj equals what? 1. We say that this probability defined is the joint probability mass function of a bivariate random variable x and y. I repeat, we explain bivariate random variable. We say this bivariate random variable must have its own distribution. And we say the distribution is what we call bivariate discrete distribution, or what we call the joint probability mass function of the random variable x and y. We say, how do we define this bivariate discrete distribution? We say when we define a probability this way, or we define a probability this way, or we define a probability this way, such that these probabilities defined all satisfy this condition. We say that this probability which we have defined is the joint PMF of the random variable x and y. So that's what we call the joint probability mass function of the random variable x and y. Okay, then we now go ahead. We are to go to marginal distribution. And before we go to marginal distribution of either x and y, it is better that we showcase with a table how this random variable x and y takes observation from the sample space. With that in mind, going about getting the marginal distribution of x and y might not be too much of a problem to us, or might not pose much confusion as it should ordinarily. So permit me to clean here while we showcase what looks like the sample space of the two random variables x and y. So permit me to clean here. Okay, I have a random variable y. I have a random variable y. I have another random variable x. This random variable x and y, they are defined on the sample what space. Okay? And this random variable takes up values y1, y2, up to what? Yn. And of course, this my x, which is a random variable, takes a value what? X1, x2, down to n. Down to xn. Let me put something like j here and put something like I here. J here means at this point, my j is 1. At this point, my j is 2. And at this point, my j is what? N. So by implication, j runs from 1 to what? To n. My j takes value 1, 2, down to n. And my I equally takes value 1, 2, down to n. Okay. But we have a function, and that function is the two-dimensional random variable x, y, defined on this sample space. So for them to take their own values, it's going to be the values of x and y. So at this point, at this very point, that bivariate random variable x, y, at this point is going to take observation x1, y1. And at this point, it takes x1, y2, down to x1, yn. That is this and this here. This and this here. this and this here. Then equally when it comes here, it takes a value x what 2 comma what y 1 here x what 2 comma y what 2 down to x what 2 comma y n. Then down to what xn comma what y 1, then x what n comma y 2 down to xn comma yn. So these are the possible values of the bivariate random variable xy taken on that sample space where the random variables x and y were ab initio defined. Okay? So with this in mind, what I just want you to remember for me here is that j runs from 1 to n. And my I runs from 1 to n. And j is talking about y variables. yi is talking about x variables. That is the only thing I want you to remember for me here. So we are now going to go over to what we call the marginal distribution of x and y, bearing this thing in mind for me. Thank you very much. So we are now talking about the marginal probability function. Marginal probability function. Marginal probability function of x and y. When we talk about marginal probability in the concept of this bivariate random variable or bivariate random distribution, we are talking about evaluating the probability of what? Of x, or evaluating the probabilities of what? Of y individually, irrespective of the fact that both of them occur in a bivariate random variable. That's what we mean by marginal distribution. Obtaining the probabilities of what? Of x, as if it were x occurring all alone, and obtaining the probabilities of what? Of y, as if it were y occurring all alone. That's what we mean by marginal distribution. So how do we define the marginal probability function of what? Of x and y? Look at what we are going to do. To define the probability, the marginal probability function of x, we write that p of what? Of xi, which of course can be written as what? P of x taking a value what? Xi is given as P of what? X equals what? X what? I intersection y taking a value what? Y1, or P of x taking a value x what? I intersection y taking a value y what? 2. Or remember that earlier when we used the table to showcase the possible values of the random variable x and y, we saw that y took observations from 1 to what? To n. It moved to what? To n. Here we just have had y1, here is y2. So or y3 or y4 or y5 down up to yn. So it's just good we say dot to p of what? X equals what? X what? I intersection y equals what? Yn. We close it, the bracket. We should bear in mind that or in probability means what? Is addition. So we are adding these quantities when y is taking a value 1, taking a value 2, down to a value what? N. And what is that thing that is running from 1 to n? What is running from 1 to n is what is j. Remember, for y. So what I'm now going to do here becomes that the whole of this thing becomes that this equals summation over that j, which is running from 1 to n, of this p of x equals what? Xi, intersection capital Y equals yj. Because I now know that this my j is running from 1 to what? To n. This is what we call marginal probability of what? Of x. That is, at a given value of what? Of x. When this random variable x takes a value what? Xi, we now get its probability alongside when y takes the value y1, y2, y3 down to what? To yn. For instance, if this x takes a value what? 1, we now say that the marginal probability of the random variable x taking a value what? 1, we now get it alongside when this random variable y takes a value y1, y2, y3 down to yn. We equally come. When this random variable x takes a value what? 2, we get its probability alongside when this y takes a value y1, y2, y3 down to yn. At the end, it will form a distribution of probabilities, which we call the marginal probability of x. Marginal probabilities of what? Of x. Now, the way we found the marginal probability of x, we can equally find the marginal probability of y. To get the marginal probability of y, this expression is going to be written this way, that p of what? Of yj, which is the same thing as p of y, taking a value yj, is going to be given as summation. We summed over j when we are talking about what? X. So we are going to sum over I when we are talking about what? Y. So we sum over what? I of p of x equals what? X what? I. Or permit me to write this way, which of course you know is the same thing. We say of what? Y equals what? Yj intersection x equals what? X what? I. We close it. So equally, what is meant here is that we are going to, assuming that this y takes a value what? 1. We are now going to get the probability that y takes a value 1 alongside that x takes a value 1, 2, 3 down to what? To n. When the y takes a value 2, we get its probability alongside when x takes a value 1, 2, 3 down to what? To n. Then we now have probabilities, different probabilities, depending on when y takes a value what? 1, y takes a value 2, y takes a value what? 3. These are what we call the marginal probabilities of what? Of y. So anytime you see this kind of a thing, described this way and written this way, that are talking about what the marginal probabilities of x and y coming from the bivariate distribution. We are equally going to take examples on them, but permit us now, first of all, to round down all these things now, so that when we are taking questions now, it will become much easier for us. So permit me to clean this while we go into what we call the conditional distribution or the conditional probabilities. This one is the marginal probability function. So we enter into what we call the conditional probability mass function. The conditional probability mass function. Conditional probability mass function. Which of course is the conditional PMF, just like what I wrote the other time. This is conditional PMF. conditional DMF, conditional mass probability mass function. When we talk about the conditional probability mass function of either x and what we are saying is this. Probability that capital X takes a value xi, given that y takes a value yj. This is defined as probability that x takes a value xi intersection that y takes a value yj all over probability of y equals yj. This is the conditional probability of x, given that y takes a value yj. So when you talk about conditional probability of y taking a value yj, given that x has taken a value x what I, we say this is given as p of x equals what x what I intersection y equals what yj all over p of x equals what x what I. That is the conditional probability of y taking a value yj, given that this x already has taken a value x what I, is given as this. Okay? So these are what we call the conditional probabilities. So when we begin to apply them, of course, that's when you now begin to appreciate them all the more. Okay? So we now move over to the next one. And that next one we are going to move over now is what we call the independence of the bivariate discrete random variable. When do we say that these two random variables involved in the bivariate random variable are independent? When do we say that they are independent? So that's what we are going to go over. So permit me to clean here. Okay, so we now say independence. Independence of the bivariate random variable. Bivariate random variables. Please permit me to use this RVS to mean random variables in order to economize that space. Okay? Permit me to bring down my curtains so that the reflection of light will not be coming into this video. I think it is better. Reflection was actually coming much from the window side, so I had to go and close it up. We are talking about the independence of this bivariate random variable. No, three things are what we look forward to happen. And if any of them happens, actually, we can just quickly conclude that the random variables there are what are independent. And what are those things? Number one is if p of x equals what xi intersection what y equals what yj equals probability of x equals xi multiplied by probability that y equals what yj. If this happens, we say that x and y are independent. If the joint probability of x taking this value and y taking this value is the same thing as the product of the probabilities of x taking this value and y taking this value, we now conclude that the random variables x and y are independent. Or we can equally look at II. If the conditional probability, if the what? The conditional probability. If probability of capital X equals xi, given capital Y equals what? Yj equals P of capital X equals what? Xi. It means that the probability that y taking up a value yj doesn't affect the random variable x taking value x what I. And that was why here the probability that x takes a value this, given that y has taken a value this, still returns probability of x taking a value xi. So if the conditional probability of what of x given y still remains as the probability of what of x taking that value, we say that x and y are independent. And of course, when we have if that p of capital Y taking a value yj, given that capital X is taking a value xi, returns p of y given what? Yj. We now say that a random variable x and y are equally independent. So these are actually some of the things we need to look forward or look at when they ask us now to check if x and y are independent. Thank you thus far for the class. We are going to clean the board and take some questions, at least to add flesh to all the skeletons we have created discussing these things with you. But I promise you, when we take a question, you end up going to appreciate it. So permit me to clean here while we take some questions. Okay. The first question we are going to take says, and I write, I target worked examples. Target worked examples. Worked examples. We want to take some examples. That question says, the following table represents. Please permit me. It's a question number 1. The following table. The following table represents the joint probability distribution. The joint probability. Permit me to write this as probability distribution of the discrete random variable of the discrete random variable x, y. I'm writing this as a random variable. That table is given as here is x, here is y, here is 1, 2, 3, here is 1 and what? 2. Here is 0.1, 0.2, 0.1, 0.3, 0.2, 0.1. So the question they ask us here is question number I. It says, obtain the marginal distributions. Obtain the marginal distributions. Please, this thing stands for marginal distribution. I want to economize this board. Obtain the marginal distributions. Question II says, the conditional distribution of conditional distribution of x given capital Y equals to 1 and I, we have probability that x plus what? Y is less than 4. That x plus 1 is less than 4. Let me use block bracket here and then use this way here. That is the question they ask us. So here is obtain the marginal distribution. Here, obtain the conditional distribution of x given 1, given that y is 1. And here, probability that x plus y is less than what? 4. So we are going to solve together with you. We'll make effort to see whether we can add flesh to the much we have seen. So solution. We begin from the I, which is talking about the marginal distribution. Marginal distribution. And then we are going to get the marginal distribution of x and marginal distribution of what? Y. Because this asks us here, obtain the marginal distributions. They were not specific of either x or what or y. But we know the formula for marginal distribution of x and then the formula for marginal distribution of y. Remember that the marginal distribution of x is given as this, that P of xi is the same thing as P of capital X equals what? Xi, which is the same thing as this summation over J of what? P of X equals what? Xi, okay? Intersection capital Y equals Yj. This is the formula for that. So we are looking at these things. Summation probability that x takes a value x1 given or intersection probability that y takes a value yj. Now we come here, of course our j here becomes, remember what we did before, here is my j, here is my I. So my j runs from 1 to what? To 2. And my I runs from 1 to what? To 3. And what marginal probability of x means? Summing these probabilities over j. Okay? So we now say therefore, I'm now coming here, I say capital P of x, this x equals, my x began from 1. So I will now say when it is equals to 1 equals, I am going to sum this probability. Look at this probability. This is the probability. And of course, you know that this probability, of course, is the joint probabilities of x and y. So I'm going to sum the joint probability of x and y over g. At this point where my x equals 1, I will turn here. My x equals 1 here. Then I'm going to sum all these probabilities over g. At this point at which x equals what? 1. Which means I have what? This is 0.1 plus 0.2, which is going to give me 0.3. I will now say P of x equals what? 2. I'm now going to sum this one, which is 0.1 plus 0.3, which gives me 0.4. I'm now going to say P of x equals what? 3. I now sum this one, which is equals 0.2 plus 0.1, which gives me 0.3. Okay? Now, the important thing that we need to note here is that after obtaining the marginal probabilities, and then you sum the marginal probabilities together, all the answers is going to give you what? 1. If you watch here, 0.3 to this is 0.7 to this is 1. So you now say that the marginal distribution, therefore the marginal distribution, you do something like this and do something like this. Okay? You do something like this. This is my x. This is my x. This is my P of x equals what? Xi. Okay, let me make it clear so I can see it very well. have this, I have this, I have this, I have this. I have that this is what is x. I have that this is p of x equals xi. So my x is began from 1, 2, and 3. This, and this. At point where it is 1, 0.3. When it was 2, 0.4. When it was 3, 0.3. This is the marginal distribution of what? Of x. The marginal distribution of what? Of x. This is this. So the moment you call up this formula with this formula, you can go a long way to do whatever thing which you want. And this is exactly what we have done here. The marginal distribution of what? Of xi. Sum it over j. Okay? And this is exactly, j runs from 1 to what? To 2. Because it's talking about what? 1. I runs from 1 to what? To 3. Talking about what? X. So this is the marginal probability of x. We want to go and obtain the marginal probability of what? Of y. So permit me to clean. So to obtain the marginal probability of what? Of y is still going to be very, very simple. We know what we are going to do. So we now say that p of y what? I or yj, which is the same thing as p of capital Y equals what? Yj, is now going to be summation over what? I of p of what? Y equals what? Yj intersection that x equals what? X what? I decided to write it this way to explain to you that they are the same thing. If you like, say probability of x equals xi intersection y equals yj, or say probability of y equals yj intersection x equals to xj, they are the same thing. If you have a set A and a set B, and you say what is the intersection of A and B, elements you are going to get are the same thing. What is the intersection of B and A? Elements you are going to get are the same thing. So their probabilities are equally the same thing. So the only important thing here that this time around we are summing over I. This same probability is here. And for us to sum over I, it means if I want to solve, I will now say probability, I now come and say probability that this my y here takes a value yj. And of course, you know that my y is begins from 1 and ends at 2. So when it takes a value what? 1, I am going to sum all these probabilities, which is the joint probabilities, at the point where my y equals what? 1. I will now come here. Look at where my y equals to 1. So I will sum these probabilities over I. Look at I over I. So this now becomes 0.1 plus 0.1 plus 0.2, which gives me 0.4. I summed all these. So I will now say P of y equals what? 2. I will sum all over these, which is 0.2 plus 0.3 plus 0.1, which of course gives me this to this is 0. Which gives me 0.6. And good enough, if you still say 0.4 plus 0.6, it will still give you 1. Which tells you that when you sum all the marginal probabilities now, the answer still gives you 1. So we now say, therefore, you do your table this way. You do here to be y. You do here to be probability that capital Y equals to yj. You have 1, you have 2. When it was 1, 0.4. When it was what? 2, 0.6. This is the marginal probability of y. The marginal probabilities of what? Of y. So I want to believe you have not had concern or problems. If you do, please hit our comment section. Tell us where you're having challenges. Surely we'll come to your aid. So permit me to clean this board while we talk about the conditional probability. When we talk about conditional probability, we write each word's formula for you. Then we also solve together. So conditional probability. Permit me to clean it. Okay, based on what we have discussed so far, their conditional probability is given as conditional probability is probability that x equals what? Xi, given that y equals what? Yj. And of course, we define this thing to be, let me economize the board, let me write it closer to help me economize the space of the board. We say that it is probability that capital X equals Xi, given that capital Y equals what? Yj, which we say is defined as probability that capital X equals Xi, intersection capital Y equals what? Yj, all over probability of capital Y equals Yj. This is what we gave earlier. Okay? Now, what we are now going to do is, this time around, they ask us to find conditional distribution of x, given that y equals 1. So they are specific, y equals what? 1. So in that case, anywhere you see yj here, it takes up a value what? 1. That's the implication. So this thing becomes p of s equals xi, given that y equals 1 equals probability that capital S equals xi, intersection that what? Y equals what? 1, all over. We have that this becomes what? P of what? Of y equals what? 1. This is what we have. Okay? So there's something that we are going to pay attention here. You see, we have xi here, and our xi began from x is 1 here, x is 2 here, x is 3 here. So we are going to get this conditional probability when x equals 1, when x equals 2, and when x equals to 3 to form the conditional probabilities. So I will now say, therefore, this is my p of this x now equals what? 1. X equals what? 1 now. Given that y equals what? 1 is now going to be, I now come here, p of this x equals 1, intersection that y equals 1, all over p of y equals 1. We need to pay attention here. This, of course, becomes, of course, when x equals 1 and y equals to 1, intersection here is talking about joint probability. You should know that. Anytime they use the word intersection, it's talking about joint probability. So we are looking for joint probability that x takes a value of 1 and y takes a value of what? 1. We return back to the table. Look at x taking a value of 1 here. Look at y taking a value of 1 here. What's their joint probability? 0.1. So the numerator here, first of all, becomes 0.1 all over. We are talking about probabilities of x, of y being 1. Pay attention here. When y is 1 here, these are all possible probabilities when this y takes the value 1. So in that case, you are going to sum these probabilities, which is 0.1 plus 0.1 plus 0.2, which is 0.4. So here is all over 0.4. And I think either this should be either be 0.25 or thereabout, and 0.1 divided by that. I wouldn't know, I don't have calculators on me. So when you want to do it now for x equals what? 2, then you now come, when x equals 2 and y equals 1, you come here. Now we are talking about x equals 2. It will now return back here. So which means it is now equally going to be that it is going to be p of x equals what? 2, given that y equals what? 1. The numerator here, this place is going to be 2 here, and this one still remains 1. Here is my 2. Here is my 1. So when x is 2, look at it here. When y is 1, look at it here. Where do they intersect? They intersected here. So the probability still remains what? 0.1. So I still have what? 0.1 all over 0.4, which I think either 0.25. Then you now come to the last one. So here x is now going to be what? 3. So when x becomes 3, given that y equals what? 1, you should be at here. And that will now give you 0.2. And then 0.2 all over 0.4 will now give you 0.5. Okay? So, and even if you come still, if you solve 0.25 plus 0.25 plus 0.5 will arrive at 1. Then you now be able now to say that the conditional, you now draw a table. Now, permit me to clean this stuff here. Permit me to clean this stuff here. You now draw a table this way, this way, this way, this way, and this way. So you now have here. So here it becomes what? My x. Here is my x. Then what you're now going to write here is now you write p of x what? X equals what? Xi. Permit me to write bold for you to understand how it is different from the marginal. Here is going to be xi, here is going to be p of what? X what? Giving xi. Sorry, x equals xi, given that y equals what? 1. This is what you are going to write here. So you now have here x is 1, 2, and then 3. Have this, and that. So you now say when this x was 1, what you got was this 0.25. So this 0.25. When x was 2, you got 0.25, 0.25. When x was 3, was the one that we mentioned with the amount. Here is 0.2 all over that, which is 0.50. So this is what we call the conditional distribution of x when y equals what? 2. I want you to try by yourself the conditional distribution of what? Of x, given that y equals what? 2. See what you are going to have. Very important. You see that with this, everything is almost clear. Everything is almost clear. So please permit me to clean the board while we attend to the last question in order to manage the size of this video. So permit me to clean here. Okay, the last question says we should get a probability that the sum of x and y should be less than 4. That one is very simple. So I say probability that capital X plus capital Y is less than what? 4. So we now come here. Of course, when we come here, we now begin 1 plus 1. If this x takes a value 1 and this y takes a value what? 1, you find out that 1 plus 1 is less than what? 4. So meaning that I'm interested in probability that x equals 1 and intersection that what? Y equals what? 1. Or when you say this plus this, it will give you 3, which is still less than 4. So, or probably that x equals 1, intersection y equals what? 2. Or when you come here and you say this 2 plus this 1, it is still 3. So it is still less than 4. Or probably that what? X equals what? 2, intersection y equals what? 1. But when you come here and you say 2 plus 2, it will now be 4. So you won't reach there. So the probability they need is this, this, and this. So which of course is equals, or means addition. 1 and 1 is here, which is 0.1 plus. 1 and 2 is here, which is 0.2 plus. 2 and 1 is here, which is 0.1. You have 0.1. So this equals what? 0.4. So this is the probability at which this is equals this value. Okay? Thank you very much for your attention and for your audience so far. Permit us to give you something which you are going to try at your convenience. In our next class, we might need to revisit them. Oh no, I couldn't have cleaned. Oh, I should clean it because we are going to a new question altogether. Please, we want you to look at this one when you go home And in our next class, you might put your questions in the comment section. Let us see what your concerns are. Okay? That question says, number 2, say two discrete random variables. Random variables x and y have p of x equals 0, comma y equals what? 0 equals 2/9, and p of x equals what? 0, y equals 1 equals 1/9, and p of x equals 1, y equals 0 equals 1/9, and finally p of x equals 1, y equals 1 equals 5/9. Then the question I says, obtain the marginal distributions of x and y. Obtain the marginal distributions of x and y. Then number 2 or II says conditional distribution. Conditional distribution of what? X, of what? X, given y equals 0. And then I is asking you determine if x and y are independent. Okay? Thank you very much for your audience so far. Try these ones and see if your answers will be correct. And do not forget to subscribe to our YouTube channel, like, share our videos, and then comment if the class is okay by you. Most importantly, subscribe after watching the videos so that the moment we provide solutions to assignments like this, or we come up with another class, you get a notification from us. Thank you very much. Till the next class, when we talk about the marginal CDF instead of the marginal probability.